For the last 50 years, the story of computing has always been the same. Smaller, faster, better. But that story, it's hitting a brick wall. A real, fundamental, physical limit that could seriously mean the end of progress as we know it. So today, we're going to dig into why and, more importantly, what's next.
I mean, it's a totally fair question, right? We've all felt it. That feeling that the speed gains just aren't what they used to be. The massive leaps we got used to have turned into tiny little steps. So what's really going on under the hood? Why is the engine of innovation all of a sudden sputtering out?
This is it. The single biggest villain in our story, the barrier to the future of computing. And it has a name, the heat wall. And let me be clear, this isn't some software bug we can just patch. Nope, this is a fundamental problem of physics, and we just can't engineer our way around it with the same old tricks anymore.
Okay, so for more than half a century, the game plan in computing was super simple. Just shrink the transistors. Smaller transistors meant you could pack more of them onto a single chip, which meant more power. That was the magic behind Moore's law. But we finally reached the point where shrinking them any further creates a problem we just can't solve. Now, the key word here is density. The problem isn't the total amount of heat a chip makes. The problem is that we are cramming so much energy into such an unbelievably tiny space that the components literally get too hot to work properly. When you get down to the atomic scale, that heat just becomes completely unmanageable. So to figure out how we get around this heat problem, we have to go back, way back, to the very foundation of everything digital. And it turns out the core of our digital world, binary logic, the ones and zeros, it wasn't some brilliant, perfectly optimized choice. It was basically an accident of history. Just look at how this all played out. It all kicked off back in the 40s with these big, clunky mechanical switches that could only be either on or off. When transistors came along in the 50s, they were just way smaller, much better switches. So we just kept the same simple on-off system. And for the next 50-plus years, the entire world of software and hardware was built on that simple two-state assumption. Until, as you can see, we ran smack into a physical wall. And this quote just nails it. We have built a global technological empire on a foundation that was chosen because it was easy for 1940s hardware to handle, not because it was the most efficient. We've been living with a constraint we inherited, and now that constraint has hit its physical limit.
Okay, so if the problem is all the heat being generated by electrical switching, what if we just stopped using electricity to do the switching? This is where the story gets really, really exciting. There's a new approach that sidesteps the heat wall completely by changing the very physical domain where we do our computing. So here's the fundamental shift. Electrical computing is all about pushing electrons around, which, creates friction and heat. But this new magnetic approach, it just manipulates magnetic fields, which is an inherently cool operation. And here's the real kicker. While silicon is really only stable in two states, on or off, the magnetic domain is naturally stable in multiple states. And trust me, that changes absolutely everything. And that ability to have more than just two states, well, it unlocks this dream that computer scientists have had for decades, multi-valued logic, or MVL. Think about it. Instead of just a 0 and a 1, what if you could also have a 2 or even a 3, all in a single tiny component? This chart just lays it all out perfectly. Look at that first bar. A standard binary wire carries one bit of information. Simple. But then move to the next one, a ternary wire using 3 states, and boom, you're carrying over 1.5 bits. Now look at a quaternary wire with 4 states. You get 2 full bits. You are literally doubling the amount of information you can send without adding a single physical wire. Okay, you gotta stick with me here, because this next part is genuinely fascinating. There's this mathematical idea called radix economy, which is basically a fancy way of asking a simple question. What is the most efficient possible number system for representing information? Is it base 2? Base 10? Well, the answer is going to surprise you. How cool is that? It turns out the most mathematically perfect, the most efficient number system isn't binary at all. It's base 3, also known as ternary. So the system we stumbled into by accident, yeah, it's actually one of the least efficient ways to do things. We've literally had it backwards this whole time, and now the physics are here to prove it. All right, so this begs a pretty obvious question, right? If this multi-valued logic stuff is so great, why aren't we all using it already? Well, people have tried for over 60 years. The answer is all about why those previous attempts failed and why this new magnetic approach finally works. First,
let's talk about the failures. Trying to force multi-valued logic onto good old silicon is like trying to build a skyscraper out of jello. It's just fundamentally unstable. See, in silicon, a state is just a very specific level of voltage. So to get more states, you have to slice that voltage into these tiny, super delicate bands. But here's the problem. The real world is noisy. The tiniest bit of electrical noise or a slight change in temperature causes those voltage levels to drift and bleed into each other, creating massive error rates. It was just way too unreliable to ever be practical. All right, so that was the silicon nightmare. Now, let's look at the magnetic advantage. It doesn't have any of those fragility problems. It's just fundamentally more robust. In the magnetic world, your states aren't these flimsy voltage levels. No, they are distinct, high-contrast magnetic fields. Think of them like the north and south poles of a magnet. They are super clear and super stable. They're highly resistant to noise and heat. So you get the best of both worlds, the rock-solid reliability of binary, but with the awesome power and density of multiple states. So what this all really means is that we're on the verge of a truly foundational shift. This isn't just about making a slightly better transistor. No way. This is about creating a whole new building block for the digital age, opening up a brand new frontier for how we scale performance. So let's just see how this all stacks up. First, you get cooler operation, which lets us sidestep the heat wall completely. Then, you get higher density, which means more logic, more information in the exact same amount of space. Then you add in greater stability and much more efficient math. It's a whole set of advantages that build on each other, creating a new path forward, a roadmap for scaling that silicon just can't follow anymore. And really, this quote sums up the whole story perfectly. For years, the smartest people on the planet have been trying to smash their way through this physical barrier. But it turns out the solution was never about breaking the wall. It was about realizing you could just walk around it by choosing a different path entirely. And that's the thought I really want to leave you with. For our entire lives, our whole digital reality has been built on this accidental foundation of ones and zeros. Now that we know that foundation can be replaced with something fundamentally better, what other assumptions are we ready to challenge? What does the future look like when we're no longer bound by the ghosts of our very first machines?